Good morning, everybody. My name is Sergey Handrikov, and this is Nikita Chumakov. We'd like to tell you about the optimization of a Boost.Asio-based network server, which we are made. Well, first of all, I'd like to tell you about our company, Yandex. Just a couple of minutes. Well, Yandex is the leading search engine in Russia. They have about 62 Russian search traffic, and they serve about 25 million unique users per day. And we are 6,000 employees. Yandex provides some personal services such as photo hosting, cloud storage, and email. Well, we are from email. Yandex email was built in 2002. We serve about 9 million users per day, and we handle about 100 of million messages which are sent and received daily. And there are about 20 internal services which are passing incoming and outgoing messages such as SMTP server, POP server, IMAP server, web interface server, and so on. So it will be nice to optimize them for better resource utilization. Well, they made some research, and we looked at the different input-output models, such as synchronous model, asynchronous model, and of course coroutine. We tried two types of concurrency. These are thread per IO service and multi-thread per IO service. And we also tried different buffers for IOs, for input and output. These are the continuous buffer with relocations. This is a standard ASIO stream buffer. And the next one is our zero-copy buffer, which allows us to receive data without copy it. Well, any question? Okay. Let's look at the models which we tried. This is the architecture of the synchronous and asynchronous server simulation. Here is a server class which accepts the connection and instantiates the corresponding connection class object. It has a thread pool. Thread pool provides threads and provides IO service objects. The connection handles the incoming data with help of RFC 2822 parser. This parser is built on the Boost Spirit. We used two different types of the stream buffer. This is the ASIO stream buffer, and this is our zero-copy stream buffer. It's pretty simple, I think. This is the configuration of a synchronous input-output model. Oops, sorry. I skipped the slide. This is the configuration of synchronous input-output model. Well, we tried the configuration with thread per connect, where we create a thread for each client connection. And we tried process per connect, where we fork the process per each client connection. Well, our coworker said, well, guys, don't lose your time for this one, because it's pretty slow. Well, but we tried. The result of our try we will see later. Okay, the first asynchronous input-output model we called 1N. This is the configuration with single IO service object and one thread per CPU core. This configuration is called N2N. Here we have one IO service object per CPU core, and here we have one thread per CPU core, and each thread is bound to the dedicated CPU core. Well, we tried to eliminate thread switching between CPU cores, and maybe to grow the grow the performance. Sorry. This model is the combination of previous two models. Here we have an IO service object per CPU core, but here we have two threads per IO service. We made it for the hyperthreading CPU utilization, and we thought that this model will give us the greater performance than previous two. Well, and now we have something completely different. This is the coroutine. This is architecture. It's very similar to previous architecture. Here is the server class. It contains threads, contains IO service, contains session which is used, parser with RFC 2822. Here are the same two different buffers, the ASIO string, a basic string buffer, and our zero copy basic string buffer. The difference are the next. The first one is the coroutine do, and the next one is read iterator. This entity allows us to process data while we receiving next part of data. On the next slide shows how it works. Well, we have some data which already received the part of data, and of course we have an iterator in the beginning of this data, and now we begin to process the data. Okay, we reached the end of the received data. Now our context will be suspended and wait for the next part of data. Okay, we have next part of data. We handle it. We suspend. And now, the same way. Okay, we handle full data from client. Of course, we can handle data and receive data simultaneously. It's difficult to show in this program, in this presentation program. Well, we used stateful coroutine. In this configuration, we used one I/O service object and one trap with CPU core. So we examine three types of the program. The first one is the Asio stream buffer. With using the Asio stream buffer. The second one using our zero copy buffer with read iterator, and the third one is the Asio stream buffer with read iterator. Any question? Oops. Well, let's see how the zero copy buffer works. Let's look, first of all, let's look how the Asio buffer works. Well, we have some memory. The first part of this memory is used by the old data, just received in the past. And the second part is free. Well, here comes a new data to be rewritten, and oops, we have no enough free memory to fit this data. Yes, what should we do?
Abort.
Nice. Yes.
Expand.
Yes, we can expand. We can. Okay, we will reallocate the memory. Yes. Okay, we allocate a new part of memory. We need to copy used memory because we shouldn't lose the data. Yes. Yes. That's right. Well, now we can free the previous memory chunk, and now we can write the data. Okay, and we have some free space. That tail. Well, now everybody happy. We got data. But here are the problems. The first problem is that the buffer allocates a bigger memory chunk while it owns the old one, which is smaller. Well, here we have memory overhead. The next problem is it copies an old data for each reallocation. Well, here we have the CPU overhead. And the last one, the application has to copy data from the buffer before its use. Because we can modify the buffer if we use a multi-thread program. Well, we need a solution for these problems. Everybody knows solutions? Anybody knows solutions? Yes?
I actually had a question. So, does that new allocation remain around for the lifetime of your application? So it only allocates if it ever has to store more data than it's ever had to store, or does it throw it away at any point and have to start over reallocating?
Sorry, one more time, please.
Yeah. So my question was, does the Asio buffer basically remain persistent for the lifetime of your application, or does it ever throw away that allocation and have to reallocate?
I see. In our case, we need to free this memory because we have a very different size of incoming data, and it's too expensive for us holds to hold the buffers with size of 40 megabytes. No, it's not good. Well, if we have around 1,000 connections, when we need to hold a storage 40 gigabytes, it's not good.
Use a ring buffer.
Sorry?
Ring buffer. Ring buffer.
A ring buffer.
Security buffer.
Ah, I see. Well, but you know, we still need copy data from it.
Yeah.
Out of it, right?
Yes, yes.
Can't you just bind the buffer to your socket, and when you do the Boost.Asio-read, you pass a Boost.Asio buffer, which is actually just a slice to the existing buffer, and then you write directly to this buffer and work on it, and when you finish it, you deallocate it.
Okay. What can you say? Ну, это самое, слайс буфера передавать в эти, не сам буфер, а срез.
What is the benefit?
You can reuse that, but as you say, what you don't want to do is you cannot hold the maximum value, but you can hold a reasonable average value. And if ever you have a very big request, in that case you will reallocate, but it's actually generally rare, and most of the time you need just a small buffer, so you can keep that, like, I don't know, 60 kilobytes, and you always have it, and that means you will have very low latency, no allocation, it's ready, you can write to it.
I see, but you know, we still need to copy.
Why?
Because we don't know.
The usual flow that the data is coming, and we need some parts of it, like some messages. These messages, for example, or usernames and passwords, whatever. This valuable data is not. Its margin is different. We cannot assume that it will be on the margins of these buffers.
Okay, I understand. You just need a subset of the data. That's
Yes,
it.
yes.
And is it
And
accepted?
we don't want to copy it.
Yes, but could you keep it alive for the duration of the treatment?
Sorry.
Can you keep, if let's say you have 1 megabyte of incoming data, but let's say you just want maybe 100 bytes,
Yes.
and you keep the 1 megabyte alive for the duration of the treatment?
In usual case, we want 100 bytes, then we want 1 kilobyte, then we want
Okay.
few kilobytes.
So
And
it's
we want to somehow to handle it.
Yeah, we can maybe talk about it later, but maybe I have an idea.
Yes.
So ASIO supports scatter, gather. So if you know upfront what the distribution of your data is, you can give it different buffers that are owned by different contexts.
Well, различные, ну, если мы знаем распределение данных, да, то мы можем типа давать. Но у нас оно неравномерно, наверное. Well, you know, we don't know which size of which data will come to us. It's extremely undetermined because we don't know which message will be.
In some cases, we know it, like in IMAP, for example, but in other protocols, we don't know beforehand the size of the messages that the client want to send us.
Okay.
So kind of backing onto that, because you can't, so ASIO doesn't own the data, right? You have to supply the container to it. you as the user of the library, you own your own data. You own the memory, and you supply the memory to it for it to use. So if you were using scatter-gather, you could receive from them, from your user, the vector, the container that contains the scatter-gather group. And as more items needed to be added, because the buffer wasn't large enough, you could then add them to the container. The user still owns it all.
Yes.
As you return it back. And so there's no additional copies that have occurred because the original data was filled. You needed more data, so you added more to the scatter-gather group.
That's how zero-copy buffer works.
Perfect.
Yeah, yes. This is our solution. Okay. Let's go to the next slide. Okay. We don't want to do relocation. We don't want to make any copy of all data, and we don't want to use it. We want to use the data from buffer directly. Well, here is some animation. Oops. This state is looks like a previous for the Asio stream buffer. Okay, here comes the new data. We just add a new memory and the received data in this memory. But here is the question: should the user of the buffer handle a list of memory chunks instead of convenient and useful, for example, vector? It's not easy. We provide some solution for it. Okay, this is the concept. Here we have the memory chunks. We call it fragment. This is the list of the fragments, and we have entity which is called segment. The segment is the representation of the, yes?
How does this differ from a deck? The standard library container.
I see. I think.
Actually, we have a problem with ownership of this data, and we would like to keep shared pointers to fragments to track the owners. Okay, so we cannot use the regular deck here.
Well, okay. The segment provides the convenient interface for the data access, and the fragment can be shared between two or more segments. This is important detail. Well, here is the zero copy architecture. Here is the basic fragment. This is the representation of the fragment. Here is the fragment list, which contains the shared pointers to the fragment. Here is the segment, and here is the stream buffer, and some other classes with which help us to access data and store data. Well, let's look closer for each object, for each class. Sorry. Okay, the basic fragment. This class contains a data. Data is it's a pointer to the memory chunk, continuous memory chunk, and it contains size of this chunk. It provides the interface to access data, so begin and end. It provides interface for size And it provides the constructor and protected method to specify to set up the memory chunk. It is important to say that this entity does not own the memory chunk. It only represents it. Here is, yes?
So what do you need the size member for?
Size memory?
The size member, so in that previous function there,
Oops. 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 Size function?
yeah, there's a size function in there. I mean, so how does this differ from just like 2 iterators or a range or something like that?
Oh, you know, this is an abstraction. This is the base class for 2 next classes. It provides some interface for these classes. You know.
The arithmetic with iterators are costly because it's not a continuous memory. Okay, it consists of some stripes.
Никит имеется в виду про этот самый, про именно во фрагменте. Well, you know, it's just this is just our selection, I think.
So, I mean,
Of
what
course.
is it abstracting if it's an abstraction? What is being hidden here?
Well, I'll show it on the next slides. Okay. Mm-hmm. Here is a derived class from the basic fragment. It called basic RAII fragment, and this entity owns the memory. It combines the fragment and the allocator. So it can allocate and deallocate memory. The allocator can be specified with the template parameter and with the constructor parameter. Okay? And here is the next derived class. It's with strange name, RAII wrapper fragment. This is the shared reference to the fragment. So we can share it via some RAII class, and we use the shared pointer. Well, with the help of this class, we can share the fragment between segments. So we still use this interface, but we have no virtual function except the destructor.
So the segment, is this like a way of saying that, you know, once all the segments go out of scope that access this memory and I can now free it? Is that the idea?
Sorry.
Sure. So you have this underlying data structure.
Yes.
You have these segments which are views into it.
Yes.
I'm wondering if the idea behind that is that if I remove this segment over here, if it deallocates, and I see that this chunk of memory is no longer referenced by any other segment, then I can deallocate that chunk of memory.
Yes.
Is that the idea?
Yes.
Okay.
Yes.
Thanks.
Okay. This is the iterator. This class helps us to use the fragments as the list of fragments as the continuous memory container. So like vector. This is a random access iterator. It contains some function to switch between the fragments when iterate through the data. Well, it contains the fragment list reference. It contains the iterator to the current fragment, and it contains the position inside the fragment. And this is the basic segment. This class provides for us a convenient interface to access the data. Okay, it provides begin, end, the begin, the end, size, empty, and it provides the append method. So the append method allows us to append one segment to another segment without any copy, of course. Well, we can match the segments with the help of the append method. Here is the top level entity basic stream buffer. It implements three interfaces. The STD stream buffer interface with xbutton, xgetton, and other. It implements the Asio stream buffer interface, and it implements our own interface for the zero copy access to the memory. Well, okay, we have a stream buffer with no copy for receiving data, and now, and now we need to get data from the buffer. Should we use STD iStream for it? No. Why?
Because it's not efficient.
There's a buffer and iStream, if I remember correctly. So you're going to do copy without knowing.
Mm-hmm. I see. Yes, and we provide our own interface to access data. This is the detach method. It detached the number of fragments before the iterator. Well, the end iterator of the buffer points to the end of received data. Well, let's look how it works. Okay, we have some stream buffer with a number of fragments, and we have the iterator. Well, it's pretty simple. We will split it. Yes? Okay, and now we can return this segment for the client. Everything is easy. Yes? But what should we do when the iterator points somewhere in the middle of the fragment? How do you think?
Share it.
Yes. Okay, we detach the first three fragments from the stream buffer, and next we create the array wrapper fragment instance, which refers to the first part of this fragment. Next step is to create the same reference into the stream buffer. Now we share this fragment, and it's alive until these two references are existed. Okay, let's go to the experiment. Well, we used two computers. Which was connected with 2 gigabits lines. one of these computers was a client, and the next one was a server. Well, on server we run different SMTP server models, simulations. Sorry, and on client we run the special client program, which provide for us a load very similar to our production load. Do you have any question? Okay. Okay, about some slide about the load. We used Boost.Asio for input-output, and the use the next setup. It was 6,000 connections, and we provide 9 kilobytes mean message size for each connection. So this is a pretty good load for our server. Oops, sorry. Here is the hardware we used. Pretty good CPU with 24 threads and 12 cores. Very big memory, and 2 Ethernet gigabit interfaces. The client and the server are identical.
Question.
Yes?
Before I thought you said that you ran 1 thread per processor.
Yes.
So does that mean 24 threads?
Per CPU.
Per CPU?
Per CPU core. Yes, per CPU core. It depends on the model, because it was 20.
Investigated different models. This is just one.
So when you say threads here, you're talking hyperthreads, right?
Yes. Of course, 12 cores only.
Right, right.
And each one has hyperthreading. Well, this is the software we used. We used Ubuntu, Asio, Spirit, Second Spirit, and the GCC 4.9 beta to be on the age of technology. Here measurements which we made from server side. We measure the RAM consumption, the CPU consumption, and the network load. Since we ran only one client, we measure the request per second on the client side. And we measured the latency on the client side. Okay, any question? Well, now we can see the results. Well, how do you think? Who is the winner? Who is the winner?
Zero copy buffer.
Yes. Okay, let's look at the results. Okay. Here is the first model, multi-threaded synchronous input-output. Well,
it's when we create one thread per connection.
Yes. And here we can see what the hit limit on the Asio stream buffer in the CPU, and the near to hit the network limit with zero copy. Here we have good advantage when they use the zero copy. We have good advantage in request per second. We have very good advantage in CPU utilization. we have a bigger memory consumption, but this is because we have more requests. We have better latency, and we near to hit the network limits.
Question.
Yes.
See, you have a 48 gig memory, and you're only ever using 175 megs of it?
Yes. Well, you know, this is only the simulation of the real server, of course, and we tried to understand: do we have any advantage from the zero copy? Oops. And this is multiprocess synchronous input-output. Here we made the process per connection, and
We created the process per connect. This is may seem not reasonable, but sometimes it makes sense because we are protected from memory faults in sub-processes. Okay.
Yeah, so if the server fails,
Yes,
then it's
yes.
just the one
It's
process,
not
the
a
one
problem.
client.
yes, they have a good robustness here. It is pretty fast. Well, we have more RAM consumption than in previous case, but still they have a good advantage from the zero copy. We are near to hit the network limit instead of hit the CPU limit. Of course, we have more CPU consumption. I think it's about, because of the forking process. Okay, this is our model one-to-end with one IO service object, and the number of threads equals to the number of CPU cores. In our cases, not CPU cores, CPU threads. Sorry. Okay, they have advantage from zero copy in the request per second. We have very good advantage in CPU consumption. We have no advantage in RAM consumption, and we have no advantage in latency. But we think that this is because they reach the network limit. We hit the network limit here. So this is our next model. This is number of IO services equals to the CPU cores, CPU threads, and number of threads equal to CPU threads, and each thread is bound to the core of the CPU. Well, we had.
I have a question.
Yes, yes.
Do you create a socket on each connection, or do you reuse them?
We created a socket, but it's really not a problem because we reuse, we send all data by the same socket.
Okay.
We opened several thousand, I think
6,000.
thousands of sockets,
Okay, so
and then we send the messages over.
Mm-hmm. Well, they have advantage, as on previous slide, they have advantage in request per second, have advantage with CPU, better than in previous slide. Yes, yes, better. They have worse RAM consumption. Okay, here is the same thing with latency. We hit the network limit. We just hit the network limit, and we have some collision.
It seems like you should try this with the fiber pipe.
Yes, yes. I think we need to review the load. I think. Yes, but you know, it's a difficult process to find the proper load. because we need to run for each load the models, and it consumes.
We can select carefully the average message size in such a way that any model would win. Okay. So we selected the typical case for us. What we see on our servers. Okay.
It would be interesting to see which of these, not the SEO versus the zero copy, but which of your I/O models would win if you had a really fat pipe. And,
Like a 10 gig card.
yeah, like a 10 gig card, and so you weren't running up against the network limit.
Ну, было бы интересно посмотреть на каждую модель, какая из моделей побеждает. Yes?
So in your simulation here, are you doing any kind of like disk access? Because I presume that you're doing something with these messages.
No. They only parse the message and get the headers from there. We don't do any I/O on disk or.
We model the SMTP. I don't know if you say that or not before. We model SMTP server here, and the client sends the message by SMTP protocol. The server parses it with Spirit parser, a very simplified part. It's a Spirit parser, and the workout is parsed by itself. If the message parsed, we think that the server is make its work. Okay.
So I get
Is
that
the result.
where they're parsing the messages, but in an actual production server, you need to do something.
Yes,
besides
Yes, of course.
To resend to the cloud service, which hosts it, which stores the data.
So it's just sending out the parsed message out through another network connection somewhere else?
Yes.
Yes.
Yes, in production, yes.
Yes.
Okay.
Well, this is the model with number of I/O services equals to the CPU cores, and each I/O service has 2 threads. Well, okay. The picture is very similar to the previous. Okay, we can look at this. They have some differences in latency, but it is not significant. Well, here we hit the network limit too, but they have good advantages in process and in the request per seconds. Sorry.
Just a quick question here.
Uh-huh.
Do you have any idea why your RAM usage is about 10 times higher while your request per second is not?
The thing it is because we can handle more connections, because we do not hit the CPU limit, and we process more connections, and we need to allocate much more memory.
I think that it's a chain of some events. First of all, we're limited by network interface here. Yeah. So the latency is high. Okay. And as latency is high, then more connections live in one time. Okay, and they host more memory. Well, maybe we shouldn't arrange the test in that way that we were limited by network. We should use less connections.
Yes. Okay. Okay. This is a coroutine, and here we have 3 cases instead of 2. The first, Asio buffer, the zero copy buffer with read iterator, and one pass is the Asio buffer with read iterator. So they have good advantage with zero copy. Here we utilize CPU in every case. Here we hit the limit of CPU in every case, I think. Well, RAM consumption is very similar, but the high RAM consumption they have in the case when they use just ASIO stream buffer. Well, latency, the worst latency of the ASIO plus read iterator, and we best network utilization is with zero copy because we near hit limit of the CPU, but still not. Well, so coroutine is show us not so good results by latency and request per seconds, but here we have a big advantage in code because we write very convenient code instead of callback chains in asynchronous input-output.
We have sequential code.
Yes.
And do you understand what is one pass? What we mean by one pass buffer?
You only scan it one time, basically.
Yes, because in other models we need to first we find the mergence of the message, and then we send it to parser. And in this way, the input parsed two times. Okay. First we find the mergence of the message, and then and second the spirit parser parses. And here we can parse it only once.
Well,
Question?
oh yes. Oops.
So, I mean, that's a pretty dramatic slide there
Yes.
for the coroutine guys. So, so I've set up systems doing both. What you just described, trying to find an endpoint and then parse, or use the coroutine to delay the parse and let's continue on. Are there other variations going on here? Are you just using the coroutine in order to do one pass parsing, or are you using the coroutine to handle more than just that?
Okay. Actually, we use asynchronous internally in Yandex. We use asynchronous model, but we have many requests that it's too complicated to write all these callbacks, and there are requests that we switch to coroutines. Okay. Because the code becomes much simpler.
Нет, здесь спрашивает, мы использовать картину для этого самого, только для обработки или для всего, вообще реализации всего, там, прием, акцепт и так далее.
Is this coroutine just handling that parse function? So in essence, you could plug that into any of your other models.
Coroutine handles the connect.
I'm sorry.
The connect.
The connection.
The connection.
It handles the connection.
So if you used it just for the parse to make one pass parsing easier, because what's disturbing about this slide, right, is your network utilization. It's horrible compared to the other methods, regardless of how hard the coding is. You would expect that you could delay the parse or do one-time parsing and still have the same network utilization.
Actually, zero copy is here is one pass parser 2. What we mean is ASIO buffer is серьезно. Объясни, что такое ASIO.
Еще раз. Well, okay, ASIO is in this case we use the only ASIO buffer with no read iterator. Okay, we read whole message into the buffer, and then we parse it.
Buff stream, okay? Stream buff. Then zero copy is our zero copy with one pass also, okay? And one pass buffer here is
This is the combination of common buffer with read iterator, which suspend the coroutine at the end of the data part until we get the next data part.
We wanted to prove that the advantage here is from zero copy and not from one pass, okay? And we see it on the slide.
Yes.
So my understanding of how coroutines work, the extra penalty that you're paying is restoring the complete stack every time you need to have a new event being processed or something like that. And I guess I'm kind of surprised that that one operation, the restoration of a stack every time there's like a new event, is causing such a huge CPU usage. Do you have any ideas to what? Is there something besides that that's causing the CPU spike with coroutine?
Okay.
We need to investigate this further. I think that maybe the implementation of coroutines in Boost.Asio is not optimal enough. And that is the reason. But we need to further investigate it.
Well, I still think in a simulation like this that you really want 100% utilization of the CPU, because it's just processing messages and doesn't do any I/O apart from that.
Well, I mean, for their setup, I mean, what we really want is the network. The network's the bottleneck that we want to hit, right? I mean, you can't do any better than 100% network.
Sure. Yeah.
Well, you can put a fatter pipe in, so, and then on the previous slides, we would have seen a different bottleneck, hopefully the CPU at some point, because we really want to know how many messages we can process, not how many messages fit in the pipe, right?
Mm-hmm.
So I think that the latency here is really concerning to me, because the one pass latency doubles essentially the other ones, while everything else is fairly consistent except the zero copy has better performance at the same CPU load. So it's interesting that all of them pegged the CPU in this case. So this, for me, this chart is more descriptive of what's going on than the previous ones where the pipe was filled and, okay, so we know that 27,000 messages per second can fit in the pipe, but we don't really know anything else.
Mm-hmm. I see. Well,
here we actually know how many get processed by the CPU.
okay. Well, actually, they have this all this software on the GitHub, and I think everybody can check out the project and try to make some research. Because okay, we have some time limits. we need to do the production, some production work. Okay, we tried to say to make some research, and this is the of course result. It's not ideal, of course. Of course, it's not ideal, because there are many ways to improve it, and that's why we are here. We just want to show our research and to get more ideas how to improve it, how to make it better. Yes.
So I guess I probably wasn't understanding. Is this using Chris's coroutine concept in Asio, or is this using coroutine from like Boost coroutine?
This is coroutine from Asio. Yes. Yes, from Asio. Stateful coroutine.
But it's the same. The Azure uses Boost coroutines. Okay. I mean stateful coroutines. Because we needed we needed for Boost Spirit parser. I don't know how to use Boost Spirit with stackless coroutines.
Any question for the slide, or we'll go to next? Okay, let's go to the next slide. Okay, we have this zero copy advantages. We have request per second advantage. We have latency advantage in case when we didn't reach the network limit. And we have great advantage in CPU utilization because we don't need copy data. What is the next? We would like to see the implementation of zero copy stream buffer in the Boost.Asio. Our implementation, we think, is far from ideal, of course. There are many places to improve it, and we just presented an idea and some proofs that idea works good.
What do you think of Boost.Asio buffer lists? Which is a list of slices that you can iterate on, like what you did. Maybe
we would like to have shared ownership.
Yes, you can. If you use a list of share pointers that you make sure they are alive for the duration of your treatment, and you just use a list of Boost.Asio buffers which are not owning the data, it works. That's what we did.
Well, it's similar, but we would like to detach some slices, okay, and we cannot do it with.
Okay, I understand.
Well, this is our GitHub repository. So don't hesitate, explore, record, modify it, and maybe we together find the best solution for it. And будешь рассказывать про клиент?
What is strange for me is that we could not detect the benefit of the end-to-end model when we set affinity and use EO servers per CPU core. Okay. In theory, it should be the benefit, but we couldn't detect it.
If you redo the same test with a double number of network cards, maybe you'll see difference.
Sorry?
If we make the same test with more network cards or 10 GB cards,
I see. If we do not hit the network limits, we will see the difference.
Okay.
Okay.
Try it.
To see the difference, you need to create one connection per client and close it, and then you will see the difference.
Yes,
that's fine.
Also. Because in your case, I'm afraid the operating system is multiplexing the different connection into one big transfer, so you might not hit the right parts of the different I/O stacks of the kernel.
Also.
There is a lot of if you really want to test how a server is doing, you need physical different clients connecting, and then you will also test your network infrastructure, but that's a different story. But if you do that, then you are 100% certain that there's not going to be some evil operating system optimization behind your back. but I don't
Yes,
know.
it is possible.
Yeah.
Well, we have about 20 minutes. Do you have any questions? Because the presentation is over now. Thank you very much.
Thank you.